Hey everyone, and welcome! Today, we are going to crack the chemical code. We're going to show you how to look at those complex-looking formulas and not just read them, but actually understand them and even predict what they'll do.
So you see something like Fe2O3, and your brain probably just goes, secret code, right? But what if I told you it's not a code at all? It's actually a language, and a language with some really simple grammar. And that's our whole goal today. We're going to learn those rules so you can read and, even write in the language of molecules.
Okay, so the very first rule, it's super simple. It's a fork in the road, really. It sets you on one of two very clear paths. It all kicks off with this, the great chemical divide.
And here's the big question. Is your element a metal or a nonmetal? That's it. If you glance at a periodic table, metals are pretty much everything on the left and in the middle. The nonmetals, they're all hanging out over on the right. And this one tiny distinction is absolutely crucial. Why? Because metals tend to make basic compounds, while nonmetals make acidic ones. That one choice right here dictates the entire game plan for naming.
All right, so let's head down that metal pathway first. We're going to see what happens when these elements from the left side of the table get together and start building stuff.
The first step couldn't be simpler. A metal bumps into some oxygen, and bam, you get a basic oxide. This is our first building block. But to name it correctly, we need to understand something called valence. It sounds technical, but it's really just a word for an element's bonding power. Think of it like how many hands an atom has to hold on to other atoms.
And check this out. This is where we see that whole valence thing in action. Let's take iron. It can have two different valences. When it's using its lower bonding power, a +2, we call it ferrous oxide. But when it's using its higher power, a +3, it's ferric oxide. See that? Us for lower and ic for higher. Tuck that little rule away, because you're definitely going to see it pop up again.
So what's next for our basic oxide? Well, you just add water. When you do, it transforms into something called a hydroxide. And guess what? Hydroxides are also known as bases. See how that works? That's exactly why we call the thing we started with a basic oxide. It all connects back.
Let's watch this play out. Our ferrous oxide becomes ferrous hydroxide. And notice the formula. That iron, with its +2 valence, it needs 2 of those hydroxide, or OH groups, to make everything balanced. Makes sense, right? And it's the same logic for the other one. Our ferric oxide becomes ferric hydroxide, and its +3 valence needs, you guessed it, 3 OH groups. The name and the formula follow a perfect logic. Okay, so we've walked the metal path and made some bases. Now let's hop back over that chemical divide we talked about and explore the parallel universe of nonmetals. As you might have guessed, they followed a really similar journey, but their final destination is going to be acidic.
Just like the metals, the journey for nonmetals starts with oxygen. A nonmetal plus oxygen gives you an acidic oxide. These compounds are so important they even get a second name, anhydrides.
And hey, you already know these. Carbon dioxide, the stuff you're exhaling right now, that's also known as carbonic anhydride. And sulfur dioxide is called sulfurous anhydride. You can already start to see the naming patterns emerging.
And again, just like on the metal path, the next step involves water. When an acidic oxide, an oxyanhydrate, reacts with water, it forms an oxyacid. The name pretty much says it all, right? It's an acid that contains oxygen.
And there it is again, our old friend, the OS and IC rule. Sulfurous acid comes from the anhydride, where sulfur has a lower valence. And the world-famous sulfuric acid? That comes from the one where sulfur is using its higher valence. It's the exact same logic we saw with iron.
So let's recap. We've made bases for metals, and we've made acids from nonmetals. We have our chemical opposites. So what do you think happens when we mix them together? This is where we get to the really classic chemistry.
It's called a neutralization reaction, and honestly, it's like a simple partner swap at a dance. You take a hydroxide, that's our base, and an acid. The metal from the base, in this case sodium, pairs up with the nonmetal part of the acid, chlorine, and the leftover bits, they just get together and form water. And the result of that little swap is sodium chloride, NaCl. You probably have some in your kitchen right now. It's just table salt. This fundamental reaction between an acid and a base is happening all around us, creating one of the most common compounds we know.
So, we've pretty much mastered naming. But what do these molecules actually look like? You know, how are all the atoms connected in 3D space? Let's switch gears from names to shapes and learn how to actually draw these things.
This right here, this is the golden rule. It's the one trick you need to know. To figure out how many bonds an atom can make, all you have to do is find it on the periodic table and look at its group number. An element in group 6 can form 6 bonds. An element in group 4, 4 bonds. It's literally that simple.
Now this is where it gets really cool, because it reveals a kind of hidden force. Why is water bent and not a straight line? Well, oxygen is in group 6, so it uses 2 of its electrons to bond with hydrogen. But the other 4 electrons form these non-bonding pairs. And those pairs actually push the hydrogen atoms away, creating that famous bent shape. The electrons you don't see in the bonds are just as important in deciding the molecule's final shape.
All right, let's put that golden rule to the test. We're going to build a more complex molecule from the ground up, using nothing but the group numbers and counting the bonds.
Let's build sulfuric acid. Sulfur is in group 6, so it needs 6 bonds. We'll put it right in the middle. We can satisfy 4 of those bonds by double bonding it to 2 oxygen atoms. That leaves 2 bonds left. We'll use those to single bond 2 more oxygens. And finally, the 2 hydrogens each attach to one of those single bonded oxygens. And that's it, a perfect stable structure built just by following the rules.
And as we draw these structures, it's good to remember there are 2 main ways atoms connect. In molecules like the sulfuric acid we just drew, atoms form covalent bonds by sharing electrons. But in salts, like table salt, one atom transfers an electron to another. This creates positive and negative ions that just stick together like magnets. That's an ionic bond.
So you see, from the simple bent shape of water to a more complex structure like phosphoric acid, the principles are always the same. Find the group number, count the bonds, and connect the atoms. It's not just a random collection of facts, it's a system with a clear key. And now you have it. We started this by asking if chemical formulas were a secret code. Now you know they're a language. If the elements are the alphabet and the molecules are the words, well, you've just learned the grammar. The only question left is, what sentences will you write?